Today, we're going to talk about triangulation of linear operators and their matrices. We know that not every matrix is diagonalizable even over the field of complex numbers. What we're going to prove today is that for any operator on a complex finite-dimensional vector space, there exists a basis in which its matrix is upper triangular. Later in this course, we will use this result to show that every square matrix over complex numbers could be brought to Jordan normal form. So this is a more specific canonical form, which is a special case of an upper triangular matrix. We begin with the following definition. Let V be a finite-dimensional vector space. A flag in V is a sequence of nested subspaces. We have V1 sits inside V2, sits inside V3, and so on, sits inside Vn, which is equal to the whole V, such that dimension of the subspace Vk is equal to k. So what we have here is we have a one-dimensional subspace that sits in a two-dimensional subspace, which sits in a three-dimensional subspace, and all this chain ends with the whole space V, which is n-dimensional in this case. The terminology of a flag comes from the following picture. In a flag, we have a tip, which is a zero-dimensional object, a point, which is attached to the staff, which is a one-dimensional object. And then to this one-dimensional object, we attach a fabric, which is a two-dimensional object. And so here we have nested zero-dimensional object, one-dimensional object, and a two-dimensional object. We say that a basis B of vector space V, so B is the set of vectors V1 up to Vn, is called compatible with a given flag if the space V1 is the span of the vector V1. So it's a one-dimensional space spanned by the first basis vector. The space V2 is the span of the first two basis vectors. The space V3 is the span of the first three basis vectors, and so on. Clearly, for every flag, we can construct a basis which is compatible with this flag. So what we do is we take this one-dimensional space and take a basis in it, so any non-zero vector. Then we have a result that if we have a basis in a subspace, then we can construct a basis of a larger space by extending the basis of a subspace. So this means that if we already have a basis V1 of a one-dimensional space V1, then we can extend it to a basis of a subspace V2 in which V1 is sitting. And so then we will get an extra vector V2 that completes the basis of V1 to the basis of V2. And we proceed inductively until we construct the basis of Vn, which is our space V, and this will give us a basis which is compatible with a given flag. Let T be a linear operator on the space V. We say that a flag is T invariant if for every k from 1 to n, subspace Vk is invariant under T. So that is T transforms Vk inside Vk. Now let the V1 through Vn be a basis of our vector space compatible with a T invariant flag. What can we say about the matrix of this operator in this basis? To compute the matrix of a linear operator in a given basis, we need to find the images of the basis vectors. Now, what can we say about T of V1? Well, we know that this belongs to the space V1 because V1 is a T invariant one-dimensional subspace. And because this subspace is spanned by the first basis vector, from here we can conclude that T of V1 must be a multiple of V1. So we can write this as A11 times V1. So in fact, this says that the first basis vector is actually an eigenvector for our linear operator. Now let's apply T to the second basis vector. So the second basis vector belongs to the subspace V2. And the subspace V2 is T invariant. So this means that the result will be in the subspace V2. And this tells us that T of V2 may be written as a linear combination of V1 and V2. And we can write this as A12 times V1 plus A22 times V2. So then T of V3 will be in the subspace V3. And then this tells us that T of V3 may be written as a linear combination of V1, V2, and V3. So it will be A13 times V1 plus A23 times V2 plus A33 times V3, and so on. Then we get the following matrix for our linear operator in basis B. So we see that the first column has only one non-zero entry. So we'll have A11 here, and everything else will be zeros. In the second column, we have only two non-zero entries. So we'll get A12 and A22, and the rest will be zeros. In the third column, we'll have three non-zero entries. We'll have A13, A23, A33, and then zeros. And so on. So what we see is that the matrix that we obtain will have an upper triangular form. So our conclusion is that if we have a linear operator with an invariant flag, and we take a basis which is compatible with this T invariant flag, then the matrix of this linear operator with respect to this compatible basis is upper triangular. Now we state our main theorem of this lecture. Every linear operator T on a complex finite dimensional vector space V has an invariant flag. So V1 sits inside V2, sits inside Vn, which is equal to V, and T of Vk is inside Vk. We point out that here we need to be working with complex vector spaces. Over a real field, this result does not hold, because here we see that if we take the first vector space, then from this calculation, it's clearly an eigenspace. Over real numbers, a rotation matrix on R2 will not have eigenvectors. And because of this, a rotation matrix will not have an invariant flag unless it's a rotation in 0 or 180 degrees. Let us reformulate this theorem in the language of matrices. We get the following corollary. For a square complex matrix A, there exists an upper triangular matrix S and an invertible matrix C such that A is equal to C times S times C inverse. So to prove the corollary, so what we do is we take B to be a basis compatible with an A invariant flag, and then we get that A will be equal to, so we take change of basis matrix C from B to E times the matrix of this linear operator with matrix A in the basis B times C E to B. So we have this change of basis formula, and then we'll have that S is the matrix of this operator in basis B, and we know that this matrix will be upper triangular, and C is the change of basis matrix from B to E. Let us now prove the theorem, and we'll give the proof by induction on N, which is the dimension of our vector space. So the basis of induction is N is equal to 1. So this is trivial. So here we take our flag just consists of a single subspace V1, which is equal to V. And because T is an operator on V, this subspace is automatically T invariant. So there is nothing to prove. Now the step of induction. So we assume that the theorem holds for operators on n-1 dimensional vector spaces over complex numbers. Let us prove that our claim holds for operator on n-dimensional vector space. We know that any operator on a complex vector space of dimension n greater or equal to 1 has an eigenvector. So T of V is equal to lambda times V. This follows from the fact that if we compute the characteristic polynomial of this operator, which is a polynomial of degree n, over complex numbers, every polynomial of degree n factors into linear factors. And because of that, we are guaranteed to have a root lambda of a characteristic polynomial. Once we get a root lambda of a characteristic polynomial, then we know that determinant of a minus lambda I will be 0. And thus, there will be a vector in the null space of a minus lambda I. And this vector in the null space will be our eigenvector that we seek. So this result is a consequence of a fact about the roots of complex polynomials. We know that in an invariant flag, the first vector space must be an eigenspace. So we take our eigenvector and turn it into our first subspace of the flag that we're going to construct. So we set V1 to be this eigenvector V and take one-dimensional subspace V1 to be the span of this eigenvector V1. Then, because this is an eigenspace, it's T-invariant. So we have T applied to V1 will be inside V1. Now we have a linear operator on a vector space with an invariant subspace. So we can apply the third homomorphism theorem. By third homomorphism theorem, there exists an operator T hat on the quotient space, where we take quotient out the invariant subspace V1. Such that we have the following commutative diagram. We have T acting from V to V. Then we have canonical projections to the quotient spaces V by V1. And here we get our operator T hat downstairs. So let us call the subspace V quotient by V1 as W. Then dimension of W is equal to n minus 1, because V is n-dimensional and V1 is one-dimensional. And by induction assumption, T hat has an invariant flag in W, because T hat is an operator on n minus 1 dimensional space. Let W1 through Wn minus 1 be a basis of W, which is compatible with T hat invariant flag. The space W is a quotient space, and the vectors in the quotient space are equivalence classes of vectors from V. So we can write that W1 is an equivalence class of some vector V2. W2 is an equivalence class of some vector V3, and so on. And Wn minus 1 is an equivalence class of some vector Vn, and all these vectors Vj are in the vector space V upstairs. Now we're in the following situation. We have a basis in a one-dimensional space V1 and a basis in the quotient space, V quotient by V1. And we had the result that describes a relation between the basis in V with the basis of a subspace and the basis of the quotient space. By this result that we proved, we have that the set V1, V2 up to Vn is a basis of our vector space V. Because V1 is a basis in a subspace, and the equivalence classes of V2 through Vn form a basis in the quotient space W. Our claim is that this basis, V1, V2 through Vn, is a basis compatible with a T-invariant flag. So this means that this basis will yield now a flag in V, which will be T-invariant, and that's exactly the claim of our theorem. So we set V1 to be the span of the vector V1, V2 to be the span of V1 and V2, V3 to be the span of V1, V2, V3, and so on. The fact that this basis is compatible with the T-invariant flag means, and so this is something that we need to prove, that T applied to any vector Vk in this basis is a linear combination of vectors V1, V2 up to Vk. And this needs to be true for every k from 1 to n. We know that this holds for k equals 1, because by our construction, V1 was an eigenvector. The T of V1 was lambda times V1. And thus, T of V1 is a linear combination of V1. What we know is that little w vectors form a basis of the quotient space compatible with the T hat invariant flag. So this means, so we know that T hat of the class of Vk is a linear combination of equivalence classes of V2 through Vk, because these are our little w vectors, right? So the class of V2 is the vector W1. Let us write this down. We have T hat applied to the class of Vk is equal to C2 times the class of V2 plus dot 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 Ck times the class of Vk. But recall our construction of T hat. So how did we define T hat applied to a class of a vector? So this was defined as the class of T applied to the vector Vk. And this tells us that the class of T of Vk, and now let us take everything to one side, minus C2, the class of V2, minus Ck, the class of Vk, is equal to the zero class. And using our definition of addition of equivalence classes, so we get that the equivalence class of T of Vk minus C2 times V2 minus Ck times Vk is equal to the zero equivalence class. But what is the zero equivalence class? So the zero equivalence class is the subspace that we quotient out. So that is V1. So this tells us that this vector T of Vk minus C2 V2 minus Ck Vk belongs to the subspace V1. And since V1 is a one-dimensional subspace spanned by vector V1, we conclude that there exists a complex number C1 such that T of Vk minus C2 V2 minus Ck Vk is equal to constant multiple of V1. And by moving the tail back to the right-hand side, we get the desired claim that T of Vk is a linear combination of vectors V1 through Vk. Now we proved that for each k from 1 to n, T of Vk is a linear combination of the first k basis vectors. This means that in this basis, the matrix of T will be upper triangular, and the flag associated with this basis is T invariant. And that's exactly the claim of our theorem. Now let us analyze our triangulation formula. We proved that any square matrix over complex numbers can be written as C times S times C inverse, where S is upper triangular and C is invertible. Let us look at the matrix S. So here we have on the diagonal, we'll have some entries D1, D2 up to Dn. We have zeros below the diagonal, and we have something above the diagonal. This formula tells us that A and S are similar matrices. This is our definition of similar matrices. And we know that similar matrices have the same characteristic polynomial. So this tells us that the determinant of A minus lambda I is equal to determinant of S minus lambda I. But the latter determinant is easy to compute because S is an upper triangular matrix and so is S minus lambda I. And we have a simple formula that determinant of an upper triangular matrix is a product of the diagonal entries. So what we get is that this determinant is equal to D1 minus lambda times D2 minus lambda times Dn minus lambda. And this gives us information about diagonal entries of this upper triangular matrix. So they are not arbitrary, but what we see is that D1 through Dn are precisely roots of characteristic polynomial of the original matrix A. So if D is a root of characteristic polynomial of A with multiplicity k, well, we know that over complex numbers, any polynomial factors into linear factors. So we say that this root D has multiplicity k if the characteristic polynomial has a factor of lambda minus D to the power of k. And then this means that D will appear k times on the diagonal of S. So we see that the diagonal of the upper triangular matrix is completely determined by the characteristic polynomial of the matrix A. So we know that over real numbers, not every square matrix may be triangulated. So we saw that rotation matrices cannot be brought to triangular form over real numbers, but over complex numbers they can even be diagonalizable. And we get the following criterion. So a real matrix A may be triangulated over real numbers if and only if characteristic polynomial of A factors into linear factors over real numbers. So this is all we need in order to bring a matrix to a triangular form. We need to have enough roots of the characteristic polynomial. Of course, if the matrix is diagonalizable, there is no point of bringing it to an upper triangular form. A diagonal matrix is a special case of an upper triangular matrix. However, we saw that even over complex numbers, not every square matrix may be diagonalizable. And triangulation is the approach that we can take for non-diagonalizable matrices. Let me give you a couple of exercises. Use triangulation of matrices to prove the following facts. So problem 1. That the determinant of the exponential of a matrix is equal to exponential of the trace of a matrix. And problem 2. So first we give a definition. A matrix A is called nilpotent if there exists a natural number n such that A to the power n is equal to a zero matrix. And prove that A is nilpotent if and only if all eigenvalues of A are zero. So this means that determinant of A minus lambda I is equal to minus lambda to the power n. So an example of a non-zero nilpotent matrix will be 0, 1, 0, 0. The square of this matrix will become a zero matrix, and the characteristic polynomial of this matrix is lambda squared. Next, let us go through a computational example of matrix triangulation. Let us triangulate the following 3 by 3 matrix. We can compute its characteristic polynomial, and we can see that it's given by this expression, so it's minus lambda plus 1 cubed. So this tells us that lambda equals negative 1 is the only eigenvalue of A with multiplicity 3. We begin by computing eigenvectors. So we take A plus I, which is A minus lambda I for lambda equals minus 1. So we get minus 2, 1, 0, minus 1, 1, 1, and 5, minus 2, 1. If we multiply the second row by minus 1 and then switch it with the first row, then we will get the matrix 1, minus 1, minus 1, minus 2, 1, 0, and 5, minus 2, 1. Then we say that new row 2 is row 2 plus 2 times row 1, and the new row 3 is row 3 minus 5 row 1. And then we get the matrix 1 minus 1 minus 1, 0 minus 1 minus 2, and 0, 3, 6. Then we switch sign of the second row. We get 1 minus 1 minus 1, 0, 1, 2, 0, 3, 6. And next we say that new row 1 is row 1 plus row 2, and new row 3 is row 3 minus 3 row 2. And this will give us the reduced row echelon form, which is 1, 0, and 1, 0, 1, 2, and 0, 0, 0. So the rank of this matrix is equal to 2. And this tells us that the dimension of the corresponding eigenspace, so lambda equals minus 1 eigenspace, is one-dimensional. So we have a single eigenvector which is given by the general parametric solution of this system. So we have x3 is equal to t, x2 is equal to negative 2t, and x1 is equal to negative t. So we have the eigenvector v1, which is minus 1, minus 2, 1. We know that when we triangulate a matrix, the first vector in our new basis is always an eigenvector. So since here we have only one eigenvector, we have to take this vector as our first basis vector. Next, we want to construct our operator t hat on the quotient space, which is C3 quotient by a one-dimensional subspace spanned by our eigenvector. To achieve this, we are going to extend a basis of V1, well, which is one-dimensional in this case, to a basis of C3. Here, a convenient tool is the following exchange lemma. Let U1 through UN be a basis of some vector space V, and let vector V is a linear combination of a basis vectors C1 U1 plus Cn Un with coefficient Ck not equal to 0. Then the following set U1, U2 up to Uk minus 1. And then we replace the vector Uk with V. And then we have Uk plus 1 up to Un is again a basis of V. And the proof of this is elementary. So since Ck is not equal to 0, we can see that Uk belongs to the span of this new set of vectors. And since we now have n vectors that span n-dimensional vector space, this is a basis. Using this exchange lemma, we see that we have the following basis of C3. So we can take V1, which is minus 1, minus 2, 1. And then we just take two standard basis vectors, E2, which is 0, 1, 0, and E3, which is 0, 0, 1. And so this is a basis of C3 that contains vector V1. And from here, so this follows that the equivalence classes of vectors E2 and E3 form a basis of the quotient space C3 quotient by V1. We proved this result that connects a basis of the quotient space and a basis of the whole space. So if we take a basis of a subspace and extend it to a basis of the whole space, then equivalence classes of the additional vectors will form a basis in the quotient space. Next, let us compute the matrix of T hat in this basis. Now, what is T hat applied to the class of E2? By definition, this is an equivalence class of T of E2. And T of E2 is the second column in our matrix. So we need to take equivalence class of the vector 1, 0, -2. Now, what we need to do now is we need to decompose this vector as a linear combination of the classes of E2 and E3. But there is a problem here, because this vector has a non-zero first component. How can we do this? Well, the trick here is that we know that the class of V1 is the zero class. This means that we can add a multiple of V1 without changing the class of the vector. So what we can say is that this is equal to the class of 1, 0, -2 plus the class of V1, which is -1, -2, 1. Since the class of V1 is a zero class. And then we get that this is the class of a vector 0, -2, and -1. And now we can easily write this as a linear combination of E2 and E3. So this is equal to -2 times the class of E2 and -1 times the class of E3. Let us do the same calculation for the second basis vector. So T of E3 is equal to the class of T applied to E3, so which is the third column of our matrix. So this is the class of 0, 1, 0. And here we get our result immediately, because this is just the vector E2. So we get the matrix of T hat as the following matrix. Well, the first column is the image of the first basis vector. And here we get -2, -1. And the second column is the image of the second basis vector. So this will be 1, 0. Now we need to triangulate this 2 by 2 matrix. The characteristic polynomial of this matrix is the determinant of -2 minus lambda, 1, -1, minus lambda. So this is going to be lambda squared plus 2 lambda plus 1. And this is lambda plus 1 squared. And this actually can be predicted, because -1 was the eigenvalue of A with multiplicity 3, and we have chosen as V1 an eigenvector with lambda equals -1. Then the prediction is that in T hat we would get -1 as the root of the characteristic polynomial with multiplicity 2. And that's exactly what had happened. So we take T hat plus I. So we get the matrix -1, 1, -1, 1. The reduced row echelon form of this matrix is 1, -1, 0, 0. And the eigenvector is going to be E2 plus the class of E3. This will give us the second basis vector upstairs. So as V2, we can take the vector 0, 1, 1, which corresponds to this class. And the second subspace in our flag will be the span of the two vectors V1, which is -1, -2, 1, and V2, which is 0, 1, 1. Now, if we quotient out this subspace, then the quotient space will be one-dimensional, and the new matrix T hat on the one-dimensional space will be a 1-by-1 matrix, which is automatically diagonal. Because of this, we can choose V3 as any vector that completes V1, V2 to a basis of C3. And now we obtain the following basis of C3 in which our matrix will be triangulated. So we take V1 as the first basis vector, -1, -2, 1. As the second basis vector, we take 0, 1, 1. And as the third basis vector, we can take 0, 0, 1. So we see that if we place these vectors as columns, then the resulting matrix will have determinant -1. So these vectors are linearly independent. So this forms a basis. And this gives us the change of basis matrix C. So will be -1, -2, 1, 0, 1, 1, 0, 0, 1. And now we write down our triangulation formula. A is equal to C times S times C inverse. And from here we get that S is equal to C inverse times A times C. And if we carry out this computation, we obtain this upper triangular matrix. As expected, on the diagonal we have -1s, which are eigenvalues of our matrix -1 with multiplicity 3. We also point out that matrix A is not diagonalizable because here we had a single eigenvalue and the one-dimensional eigenspace. The triangulation procedure that we discussed today is not particularly effective, and later in this course we will find a more efficient way of bringing matrices to Jordan normal form, which is even a better form than a triangular form of a matrix.